So we are now at a point that we actually get to start analyzing data. And the way we're going to start by that is by going through probability distributions. So we spent some time learning how to calculate probabilities, but now what kind of information can we get based on these different scenarios that we're going through? So we're going to first start with some definitions because these are super important to us. The very first one is a random variable. So a random variable is, hopefully you can get it from the name, it's random and it's varying, but it's a variable that has a single numerical value determined by chance for each outcome of a procedure. Okay, that's the kind of thing we want to be working with. We need lots of numerical data. And the way we're going to typically denote a random variable is the same way we've denoted a variable every other time before. It's typically denoted by X. So let's look at two different examples and see, are they random variables or not? So if X is the number of females in 2 births, well, it's the number, the key being that number of females. I need a numerical value. So in this case, indeed, this is a random variable. X in this case could be 0 females in 2 births, 1 female in 2 births, or you could have 2 girls, okay? So we're gonna continue to work with this example kind of throughout while we're building all this knowledge, and then we'll do a full example at the end as well. But if I change X to be a country, in this case, this is not a random variable. So if you think about the values X takes on, it would be something like the United States, Spain, England, things of that nature. In that case, X is not a number, okay? And I need it to have a numerical value, okay? So everything we're gonna be working with for pretty much the majority of this semester is going to be random variables. So it's a situation where you have a numerical value describing some type of context, and then we're going to analyze it from there. So from here, once we have this random variable, it's got all of these potential outcomes. So in the case of females, number of females in 2 births, you have the outcomes 0, 1, and 2. Now the thing is, there's a chance that you can have each of these values. The way we're going to be able to visualize that chance is using a probability distribution. So a probability distribution is a description that gives a probability for each value of a random variable. And the way we're going to denote that distribution is by using P of X, okay? So we're going to work with the same example, the number of females in 2 births, and we're going to do it in 2 different ways. We're going to do it using a table, and then we're also going to display it in a graph, which is really going to take on the shape of a histogram. So we call those graphs the probability histograms. So we're going to start by going through the table because this is a situation we individually can calculate the probabilities. So you can go through every single event if you want, but really there are 2 events. Okay? If you think about the case of there being no females in a birth, that would mean your first situation or your firstborn has to be a male, your secondborn has to be a male. And then we're going to assume that it's equally likely to have a boy or a girl. So you have a 1/2 chance of getting a male the first time, a 1/2 chance of getting a male the second time, which leads to a 1/4 chance of you having no girls. So the probability of having no girls is 0.25. Okay? So the way I would describe that on my histogram is you have your side labels, which you can't go past 1. So this first bar ends at 0.25. Now, if you consider the chance of having 1 girl, Well, again, you're having 2 kids. So it could be that the firstborn is a girl and then the secondborn is a male. Or there's another way that this can happen. Your firstborn is a male, your second is a female. And either way, they have a 1/2 chance. So really there is a 1/4 chance of this situation, a 1/4 chance of this situation. So adding those 2 possibilities together give you a 50% chance of having 1 girl, okay? So when I go to then draw my histogram, this bar would jump up to 0.5. And then last but not least, the chance of having 2 girls would mean you have a female and a female, 1/2 chance of getting a female. So again, there is a 1/4 or 0.25% chance of having 2 females. And so for my distribution, I would go ahead and draw that bar to 0.25. And then we always like to shade in those bars to give that variation and to make it more prominent. Okay. So these are 2 ways that we can display our probability distribution. A table, which gives you the true numbers, or you get that histogram to kind of be able to see what is more likely, okay? So even within random variables, we have 2 different types that we can actually talk about. We're gonna start with the simpler of the 2, but realistically, a lot of the same things work for one as they do for another. It's just kind of a generalization. So the first, in this case, when you have just a set number of outcomes, this is called discrete. So a discrete random variable has a collection of values that is finite or countable. Now, countable is a little bit of a weird situation. We're not going to dive too deep into it, but the idea is basically you have nice counting numbers, because technically you could keep having kids over and over and over and over again. So this realistically could continue on forever. But it's not taking on every single value in between. I can't have 0.5 of a birth. So in this case, it is going to be finite, but countable basically means it's counting numbers that can continue on indefinitely. So as a good example of this, the last example is a discrete random variable. There is a finite value or a finite number of outcomes. The other type, which is more complicated, is a continuous random variable. So a continuous random variable has infinitely many values, and that collection is not countable. So this is something you can take on every single number between 0 and 1. So unfortunately, a lot of things are going to fall into this continuous random variable because it really depends on how precise you get your measurement down to. So to give you some examples of this, temperature is often considered a continuous random variable because you can get such precision with certain instruments that you can take on almost every decimal place that you want. Same thing with height and with weight. You can take every value in between because it just depends on the precision of your measurement tool, okay? So for now, we're gonna start working with discrete random variables, but we will get into continuous later on. So when we're dealing with this probability distribution, there are gonna be some key requirements that we have to satisfy for it to be a probability distribution. So the first is that the random variable X is numerical and all of the associated probabilities are also numerical. So we're going to show this is satisfied with this same example of the number of females in 2 births. If I look at these outcomes, X itself is numerical, which is great. And then also the probabilities are numerical. So X takes on numbers and the probabilities take on numbers. So P of X is also numerical. So good, my first requirement is satisfied for this example. The second thing you need is the sum of P of X to equal 1, where this X assumes all possible values. Basically, all that's stating is your probabilities better add up to 1. It better be every scenario possible. It shouldn't add up to 0.75 because then 25% of your data is missing. So what situation is not accounted for? And then with rounding, of course, it might be 0.999 or it might go a little bit over. That's not the end of the world, but it should be very, very close to 1. So in this situation, I have 3 outcomes only. This better account for every possible situation. My probability of one of these events happening better equal 1. So when I sum up these probabilities, my first is 0.25. If I add my next probability of 0.5, that's 0.75. And then if I add one more quarter, indeed, it sums up to 1. Okay? So I will always fall into one of these situations where there's no females, 1 female, or 2 females in those 2 births. The third hopefully makes sense, but basically you want the output of each of these probabilities to be greater than or equal to 0, but also to be less than or equal to 1. There's no way you can have a negative probability of something happening, and there's no way one of these situations should be more than 1, which is 100% probability. So if I look at each of these outputs, the probability associated to no females is 0.25. That definitely falls in between 0 and 1. The probability of 1 female is 0.5, which is also definitely between 0 and 1. And then the probability of 2 females is 0.25, which also is between 0 and 1. Okay? So these are the 3 requirements that we need to happen for these probability distributions. If one is not satisfied, it is not a true probability distribution. So then once we have this probability distribution, we can actually get a lot of insight for it. So we talked about finding mean, we talked about finding standard deviation. We can actually do that for these distributions as well. So we're going to start with the mean for a probability distribution, and we're going to continue working with this same example. If you think about the mean, that would be adding them all up, dividing by how many you have. But in this case, there's an associated chance to that amount. So the way we find the mean is we still essentially add up all of those X values, but we need to times them by their associated probabilities. So you sum up the chance of no individuals or no females times its chance, the 1 female times its chance, the 2 females times its chance. So we add all of those together. The other thing that you might notice, maybe if you've seen this before, have taken our MGF 1100 or MAT 1100 class, this is also called the expected value. And hopefully that name makes sense. It's what you would expect the outcome to be in this situation, what is most likely to occur. So for the number of females in 2 births, if I go to find this mean, I need to sum up each X times its probability. So that means I take my first value for x and I times it by its probability. My next value for x is 1, times it by its probability. And then my final value for x is 2, and we multiply it by its probability. Now really in this first one, I don't need to do anything because 0 times anything is 0. But just for good measure, this would be 0 times 25%. Then it's 1 times 0.5%. And then 2 times 25% again. I like to switch over to using parentheses instead of using a dot here because I often confuse that with the decimal place. Again, just a personal preference. So 0 times 0.25 is 0. 1 times anything is the anything you had. And then 2 times a quarter is also 0.5. So adding these together give you 1. Okay? So this means the mean of this probability distribution is 1, and we would expect in 2 bursts for there to be 1 female. When we go to find the variance, this one's a little bit more complicated seemingly. And then you can find the standard deviation once you have the variance, but it actually simplifies to a really nice formula. So if you think about us finding standard deviation or variance before, what you would need to do is you would need to take x, you would need to subtract the mean each and every time, square it, and then you had to go through and divide by the number of values. Well, in this case, what we're actually going to do is we're going to toss in those probabilities because, again, there's a chance. And then we're going to also sum these up, okay? We're not so much worrying about dividing by the number of values because that's actually taken care of within those probabilities. But doing this would definitely be really tedious, so it actually simplifies quite a bit. If you distribute this out, you'll see there's some extra terms that happen here, but because of really nice stuff with the probability distributions, what ends up happening is you really get to use the mean formula. So you get instead the variable squared times p of x. You sum all of that up, and then once you do that, you go ahead and subtract the mean squared, okay? So to show you with this example how to actually apply this formula, we're going to sum up the values of x squared times their probabilities. And then once I do that, I'm going to subtract the mean we just found squared. So it's the same kind of formula. You really get to use exactly what you have right here. The only difference is these first components are squared. So my first value of x is 0. So we're going to take 0 squared times its probability. Next value is 1. Square that times its probability. Next value is 2. Square that times its probability. And then once I do that, I subtract my mean, which is 1 squared, okay? So filling in what each of these are, 0 squared is 0, probability of 0 is 0.25, 1 squared is 1, probability of 1 is 0.5, 2 squared is 4, probability of having 2 females is 0.25. And then 1 squared is just 1. So multiplying these out, 0 times anything is 0, 1 times 0.5 is 0.5, and then 4 times 0.25 is 1. And then we want to subtract 1. 0.5 plus 1 ends up giving us 1.5, and then we subtract 1, leading us with a variance of 0.5, okay? Now, once we have the variance, if you want to find the standard deviation for a probability distribution, all you're going to do is take the square root. That's why we started with variance, because unfortunately the formula for this is disgusting looking. So we sum up x minus the mean squared times those probabilities, and then we take a square root. But again, that inside formula is much simpler. We go ahead and sum up x squared times the probabilities, and then we subtract the mean squared, and then from there we take a square root, okay? But really, just in that example continued, we already found the variance was 0.5. So my standard deviation is the square root of that, which is about equal to 0.71 when you plug it into your calculator, okay? All right, so once we have this, we remember hopefully when we were talking about whether something was significant or not, we were talking about within 2 standard deviations of the mean. So the same kind of rule of thumb is going to be used to determine if a value is significantly low or significantly high. We find that mean for the probability distribution, and then if we add 2 standard deviations, it gives us the cutoff, and anything over here is going to be significantly high. And then if I subtract 2 standard deviations, anything over here is going to be significantly low. And then all the stuff in between is just typical data. It is not significant at all. Okay? So using that same example of the 2 females and 2 births, we want to see, is having 2 females and 2 births significantly high? So we figured out our mean was 1. That standard deviation is 0.71. So if I want to look at the significantly high numbers, I'm going to go ahead and take that mean and add 2 standard deviations. My mean is 1, my standard deviation is 0.71, and I'm going to trust you can plug this into your calculator. That gives you about 2.42. And then just for good measure, if you wanted to find the significantly low data value or that cutoff, you would subtract 2 standard deviations, which gives you negative 0.42. So anything that falls within these 2 values is considered normal or not significant. So really, this is kind of an interesting example because none of the values are significant. They're pretty common. So you can't possibly have more than 2.42 births in 2 births. It's impossible. So here within this, no, this is not significant because 2 is within 2 standard deviation of the mean. So it is not significant at all, okay? So really everything else we've already learned still applies. It's now we just have a little bit more work that we have to do to find the mean and to find that standard deviation. So let's do just one more example, and we're gonna go through basically the whole process again and figure out these different components. So we're told households are randomly selected and partitioned into groups of 4. From those 4 groups, the random variable X is the number of households with a printer. So essentially, once they randomly pick those 4 people or those 4 households, your possible outcomes were none of them had a printer, 1 household did, 2 did, 3 did, or all 4 did. So the first thing we want to ask, does this table actually give us a true probability distribution? So the first thing I need is that X itself, my random variable, is numerical, and all of those probabilities are numerical. So both X which has the values 1, 2, 3, 4, is numerical, and it's discrete. So fantastic, that's good. My values of P of X are definitely positive and less than 1 for each value of X. So that's amazing. And then the last thing, I need to make sure this accounts for 100% of my possibilities. So if I go through and I sum these probabilities, I need to add 0.26 plus 0.146, 0.339, 0.357, and 0.132. And I'm going to trust you can add all of these up, and it does give you 1. Okay. So indeed, my 3 criteria are satisfied. So yes, this is a probability distribution. Okay. Now that we know this is a probability distribution, we want to find the mean of this random variable x, and we're going to round to 1 decimal place. So to find my mean, again, what I need to do is sum everything up and divide by the number of samples I have. But instead of dividing by the number of samples, we're really multiplying by those probabilities, because that kind of takes it into account. So in this case, 0 households could have a printer, and we want to times it by the probability of that happening. 1 household out of 4 could have a printer, multiplied by that probability. 2 households times its probability. 3 households times its. And then finally 4 households times its probability. So in place of each of these values, I'm going to go ahead and just use those values in the table. So P of 0 is 0.026. P of 1 is 0.146. P of 2 is 0.339. P of 3 is 0.357. And finally, my probability of 4 is 0.132. Okay. So going through and multiplying these, well, 0 times anything is 0. 1 times anything is itself. When you do 2 times 0.339, you should get 0.678. 3 times 0.357 will give you 1.071. And finally, 4 times 0.132 is 0.528. Adding those together gives you 2.423. And then they want to round to 1 decimal place, so I need to look at the next number. 2 tells me I do not round up. So this is about 2.4 households. And again, this is that expected value, so you would expect around 2.4 households out of 4 to have a printer. Now we want to find the standard deviation of the random variable x, and we want to round to 1 decimal place. So I'm going to start by filling in that formula. We're going to start by finding the variance, so I don't need to write a giant square root every single time. And the easier way to find this is we really do the same formula for the mean, but change that to x squared. And then we subtract the mean squared. So again, I'm really going to copy all of this. The only thing that changes is those values in front become squares. So we need 0 squared times the probability of 0. 1 squared times the probability of 1. 2 squared times the probability of 2. 3 squared times the probability of 3. and 4 squared times the probability of 4. And then we need to subtract the mean household squared. And here's where I'd recommend not using the rounded number, actually use the 2.423. You should have tolerance allowed in your homework, but if you can use more decimal places, the better to start. Round at the very end. So to use these probabilities, I'm just going to go ahead and copy them from here because again, it's the same thing except the front now is squared. So this is 0 squared, which is 0 times 0.026. 1 squared is 1 times 0.146. 2 squared is 4 times 0.339. 3 squared is 9 times 0.357. And 4 squared is 16 times 0.132. And then if you plug in 2.423 squared, I don't have room at the end, but we're going to subtract 5.870929. And then from here, I'm going to trust you can plug all this in your calculator. It should give you 6.827. And then when we subtract 5.870929, this gives us 0.95607. So this is our variance. I'm again not going to round yet because we need to find the standard deviation. And to do that, we just take the square root of the variance. So if you plug that into your calculator, you'll see this is about 0.978. And we want to round to 1 decimal, so this is the one that could change. Because this is a 7, it tells me to bump up the 9. Well, when you bump up a 9, it really bumps up the decimal before that as well. So my standard deviation is about 1, and then the units on this are the same, 1 household. So this is our start to probability distributions and how we can find those key factors from it. From here, we're going to step it up and talk about specific types of distributions as well, and really put our focus on something called our normal distribution.